Welcome to the second part of Chapter 10. We are continuing on our discussion of radical halogenation. So we know that if we treat a sp3ch with Br2 and light, that we can replace the hydrogen with a bromine. We also get a bit of a side product of HBr. This can create a problem. When we look at starting materials that have other functional groups, there might be competing reactions. For instance, we know if we have, let's say, a double bond here, and we treat this with Br2 in dark or in light, what is going to happen is we're going to get an addition reaction. And since that one doesn't need to be initiated by light, that is going to happen pretty fast, and we aren't going to necessarily get the radical halogenation on an sp3 carbon that we would want. So we're going to talk about ways that we can handle these competing reactions. So if you look over here at your slides, there's a discussion about the allylic position, and this is not very surprising that the lowest BDE or bond dissociation energy is at the allylic position. This has to do with where would be the most stable radical. So the radical is going to be most stable here because not only is it secondary, it is also allylic, right? So this would be more stable than this. This one would be less stable. Putting the radical on the double bond would be even less stable. That you can see that has the highest bond association energy. So we would expect a bromine to add here. However, that double bond creates an issue, right? Because the bromine itself would react with the double bond. So when we think about this reaction, let's say this is what we want, but we know that the addition of Br2 to the alkene is competing. We have to come up with an alternative solution, and that is to use N-bromo-succinimide. This is something that we used in lab already, NBS. NBS and light works the same as Br2 and light. So this provides our bromine radical instead of using Br2. So here is what NBS looks like. All right, we have succinimide, which is this 5-membered ring with nitrogen and 2 carbonyls, and it's bromosuccinimide because there's a bromine attached to the nitrogen. This bond is homolytically cleaved in the presence of HV, in the presence of this particular wavelength of light. So you can get a bromine radical without a large amount of Br2 present. All right, so this keeps the HBr and Br2 levels low, right? Because HBr and Br2 would both react with a double bond. So what is going to be the most reactive species around will be the bromine radical. So that way we could have bromine adding to the allylic position and keep the double bond intact, right? It sort of protects the alkene by keeping Br2 and HBr levels low. Now, once the bromine radical is formed, it goes into the propagation steps, right? You have the hydrogen abstraction. You make the carbon radical. The carbon radical performs the halogen abstraction, right? Picking up the bromine. And this propagates the reaction even further because you are left with a bromine radical, which can react with another molecule of your organic compound, right? And it can keep itself going. So you are going to make some HBr in situ, and you will make some bromine, some Br2 in situ. Now, how did we make the Br2? Well, a termination step, right? We know that if a bromine radical is formed from the NBS, and before it runs into this molecule, if it runs into another bromine radical, well, then the termination step is going to form Br2. You're just not going to have very much of it in solution. So if we can keep those amounts low, we can preserve that double bond. Right? There may be some impurities, some byproducts where you lose that alkene, but if those concentrations are kept low, we will get a major product of radical halogenation. Now, something that can happen when we have an alkene, because that allylic position is more stable. And why is it more stable? It's more stable because of resonance. You can get two different products. So when you have here we go. When you have a symmetric double bond, like with this starting material, whether the, you see the two different resonance structures, whether the radical is here or here, you wind up making the same product, right? It's a cyclohexene with a bromine at position 3. But if you have an asymmetric double bond that gives you two different radicals, right? The bromine could add to either one, and it could give you two different products. It's, let's see, I was going to compare it to a reaction from organic too, but that would be so silly, so I will not do that. If we are going to use NBS and light here, we know that the bromine radical, so I'm going to go ahead and bring this in. NBS and light are being used. We know that the bromine radical is going to abstract this proton. It's in the tertiary position. It is also going to give the allylic radical, which will be the most stable. So I'm just going to flip that around there. That's going to give this allylic radical here and some HBr. This is stabilized through resonance, as is drawn on the slide, but I really like to draw too. There we go. Right? These are just resonance structures, meaning neither one of them is really complete. Right? Both of these are allylic radicals. The tertiary one, of course, is more stable, but they are both part of the equation. Right? So it's like when you have a plus charge or a minus charge in resonance, and that charge is shared or delocalized. In this case, this unstable radical is shared by two of the carbons. So both of those carbons are actually going to be reactive. So the bromine can add to either position. Right, the next step would be this radical, either one reacting with the little bit of Br2 that's in solution. So either one of those carbons could do that reaction. So that's why you get not only the bromine adding to that tertiary position, but you get some of this other product that is based on the resonance structure. I know there's at least one practice problem in your homework where you're going to have to predict both of these products. Okay, so you want to make sure with this reaction that you are prepared for both Br2 and light and NBS in light. And you need to know why NBS in light can be important. You need to know the difference between Br2 in light and just bromine and a double bond. If you are trying to add bromine to an alkane, that light is critical. If you leave it out, that would not be full credit. Okay, so moving away, that is our new reaction for this chapter. We have a couple more things to go over. This we're going to go over really quickly, mostly just because I think this is an interesting topic. I don't know about you guys. I know when I was a kid, the ozone layer was all the rage in the news. And the ozone layer is so important because it protects us from dangerous radiation from the sun. O3, right, which there's a resonance structure to be had here, but it's 3 oxygens and a resonating double bond. It is created and destroyed, so we have this cyclic reaction here in the upper atmosphere. There's no net reaction, but what happens in this cycle is a conversion of energy. So harmful UV radiation from the sun is converted into heat. And so if we didn't have the ozone layer, the amount of UV radiation coming into our planet from the sun would kill us. And so having that O3 there is really important, right? So it is initiated by the UV radiation, and it gives O2 and an oxygen radical. And then these two molecules, these two species will react with each other, right? So light causes the forward reaction. And then an oxygen diradical is very reactive. So these will react to reform the ozone and give off heat. So it won't give that same UV radiation back. So it's a really good way to convert UV to heat energy. It's spontaneous because entropy is increased, and that is because, as you see here, heat is a more disorderly form of energy compared to light. So this is spontaneous and goes in this sort of clockwise direction. So that being said, we all now can appreciate ozone. We appreciate the ozone layer for doing its job, protecting us. We could see why people might be invested in saving the ozone layer. So you might be thinking, saving it from what? This was something that I remember as a kid being really big news, where ozone depletion being a significant environmental problem. And there are different chemicals that cause that. Chlorofluorocarbon, CFCs, are definitely something I remember hearing about. You have, a handful here to look at. These are all freons. And when these light chlorofluoro alkanes reach the upper atmosphere, they also react with UV, but they produce chlorine radicals. So CFCs, when they are absorbing that same UV radiation that the ozone does, produce chlorine radicals. Now, it's the chlorine radicals that are a little pain in the butt, right? When chlorine radicals form, chlorine radicals will react with the O3, and then you don't get the O2 and the oxygen radical, which would react to reform O3. You get these little chlorine oxygen radicals. You get O2 as your main product and more chlorine radicals. So just a small amount of chlorine radicals can go up into the atmosphere and eat through a lot of ozone, right? When the ozone isn't reformed in this chain reaction. So we want to limit these chlorine radicals that are making it into the atmosphere and destroying the ozone. And so one fix to this when CFCs were then replaced with fluoroalkanes. HFCs or HFAs, alkanes or hydrofluorocarbons, they're not as harmful as CFCs. They're still greenhouse gases, so they still have issues that we want to be thoughtful about, but they don't produce those really harmful chlorine radicals. So this is just a really interesting radical reaction with some very important applications. Another radical reaction that I just want you to be aware of. You don't need to know this mechanism, so we'll skip over the slide that it shows up in, is autooxidation. So autooxidation is something that can happen when organic compounds react with O2 in the air. If they can form hydroperoxides. And so why do we care? It's a really slow process. Well, we care because hydroperoxides can be dangerous. Hydroperoxides can be explosive. And so if something very slowly is forming peroxides, it may cause it to have a very low shelf life, right? Meaning you don't want to keep this around because it becomes dangerous over time. And so it's important to know what kind of chemicals are peroxide formers and how fast. And so this is the mechanism. If you've just really been enjoying mechanisms, you can get into it, but you don't need to know this one. So you can skip right over that. For one that is a big deal for us, ethers. Ethers are particularly susceptible to autooxidation, and that means this reaction, which is generally quite slow, is a little bit faster here. So let me tell you a little bit about my experience with this. Diethyl ether is an awesome solvent. This is one that we're going to learn a lot about, say, in Chapter 12 when we look at something called a Grignard reaction. This is the solvent you want for that reaction. We do that type of reaction in organic too, and yet we do not have this solvent. The reason is this has about a 6-month to a 1-year lifespan, because once you open it and you expose it to O2, it starts to form the hydroperoxide. Again, ethers are very susceptible to this. And so if you don't use it quickly enough and it forms hydroperoxides, it can be dangerous, or it can be very expensive to get rid of, because once something has formed peroxides, the waste company have to handle it differently. So there's a couple things to do here. When I used to use ether as a solvent, we would buy it in small bottles. We would make sure to put the date on it, and we would get rid of it. Why don't we use it in our labs then? Well, because it would be used for one lab once every 6 months. So I would have to buy the exact right amount and then deal with getting rid of it. So we use other solvents, which are maybe not as great, but are safer, right? So there's always these decisions when you work in a lab. You are balancing out yield, you are balancing out toxicity, you are balancing out how fast you're going to go through things. And so it's important to know some of the other reactions that can occur. It's one of the reasons why I'm very adamant in lab that you keep bottles closed, because O2 can react with things. It is also why you might see dark containers. If you notice, a lot of our chemicals in the lab are in these dark brown amber bottles. That is to prevent light from accelerating the autooxidation process, right? It's to keep out that ever important HV, right? We know that light can initiate these radical processes. And so a lot of times chemicals come in these dark bottles to keep the light out. I've gotten ether in either amber bottles or even completely opaque silver bottles. Hydrogen peroxide is light sensitive. That's something, if you've noticed, you buy it at the store, it comes in an opaque brown bottle. That's why. It is to prevent light from accelerating that oxidation process. Another, let's see, radical reaction that affects you is auto-oxidation of, what are these called? Unsaturated fatty acids, right? So your unsaturated fats have double bonds, right? This is a triglyceride here. You have all of these carbon chains. These are your fatty acid chains on your ester linkages. You'll definitely look at these in biochem. And these unsaturated bits are more easily oxidized than if there was a totally saturated fat. That's why a lot of your unsaturated fatty foods have a lower shelf life. This is what causes food to become rancid, causes food to become toxic, is this radical reaction. Oh, sorry, I put my pen down. There we go. And, right, think about what happens when you open a banana or slice open an avocado. What immediately starts happening, right? I'm not going to try to draw it, but let's say we have avocado suddenly exposed to O2. It's immediately turning brown, right? We go to brown avocado. And what is something you can do to prevent that from happening? Have you ever made guacamole? What is something you have to put in it keeps it from turning brown? Maybe you put in a little bit of lime or lemon juice. Do you know why you do that? You maybe just were thinking, well, it's delicious, Dr. Jones, why would I not? Or it keeps it from turning brown. Why does it keep it from turning brown? It's because, and I'm going to skip over those two for just a minute. It's because vitamin C. Vitamin C is a natural antioxidant. It reacts with the oxygen radicals to prevent them from reacting with the avocado fats. At least slows it down, right? It's a competing reaction. Antioxidants that are put into unsaturated fatty foods are preservatives, all right? So a lot of times people read the labels, and you'll see this all over, food products and marketing, like, oh, it has chemicals in it. Well, some of these chemicals are there to keep the food shelf stable longer. So things like BHT and BHA, these are preservatives. They are radical inhibitors. Vitamin C and vitamin E are natural radical inhibitors. They work by reacting with radicals, making a much more stable radical, right? It has lots of resonance here. And then keeping the food, the saturated fat, from reacting and making those peroxide products, which are toxic, right? Which is when your food goes bad. Something like vitamin E, if you're familiar with that one, you know that's in a lot of like skin and hair products. It's the same idea. It is to prevent aging. Antioxidants are good for in anti-aging lotions and serums and whatnot, because again, it is a radical inhibitor. It will react with the radical, make something more stable, keep it reacting with proteins and fats and things in your face or in your body. So that was a nice little interlude through some radical reactions that are important to us just as like humans. This is the last, let's get a whole new slide here. This is the last mechanism you actually have to know for Unit 3. And so I want us to remember the reaction of HBr and peroxides with a double bond. We know this is an anti-Markovnikov addition reaction that is going to put an OH on the less substituted side. So now we didn't talk about that mechanism in Chapter 8, We saved it for chapter 10 because it is a radical reaction. This is an interesting one because it has 2 initiation steps. The first one is the peroxide. This is why the peroxide causes this different different regiochemistry. When you have heat or light, and so we don't need light for this reaction to happen. The peroxides will be initiated with even just a little bit of heat. You get that homolytic cleavage and you make 2 oxygen radicals. So it doesn't really matter what the R groups are or if they are H's. It is that oxygen-oxygen bond that breaks. Even the smallest amount of that RO gets initiated and it will perform the hydrogen abstraction. So it will react with your HBr and you'll get a little bit of alcohol side product, but you will also form a bromine radical. So instead of the addition reaction happening where, let's say, the double bond, don't write this down, just follow me here. Instead of the double bond acting as a base and picking up the proton, which is a quick reaction, a radical is so much more reactive than HBr, right? Radicals are very unstable. They want to react. It's going to react first. So instead of the hydrogen going on first, the bromine goes on first. So it is still led by what's the most stable intermediate. It's just the bromine goes on before the hydrogen. So you have your little bromine radical and you have your double bond. And the bromine goes to the less substituted side because in that first propagation step, it leaves the most stable radical. It puts the radical on the more substituted position, right? And then when that radical comes into contact with the HBr, we get another hydrogen abstraction, and the hydrogen goes on second. Then we wind up making more bromine radical. Well, we make our product. We make more bromine radical, and that bromine radical can react with another molecule of alkene, right? So you don't need much of this at all. You don't need much of that peroxide at all, which is why when this reaction was found by accident, right? The person that discovered this reaction was trying to do this. Was trying to add bromine across a double bond and assumed it would go to the more stable position, the more substitute position. However, they got the anti-marked product, and it was so surprising that they investigated what happened, and it turned out dirty glassware. They had some glassware with a little bit of peroxides left in it, and those peroxides caused this reaction here to happen. So sometimes we make a mistake and learn something new, right? But you really have to go investigate what happened. Then if we wanted to think about termination steps, any radical that was made in this reaction could bump into any other radical. So your RO radicals could bump into each other and make more peroxide and just go back. You could make a little bit of Br2. The bromine and the oxygen could bump into each other, your carbon radicals as well. However, what radical is going to be there in the greatest abundance? Well, it's going to be bromine because bromine is made in a propagation step. So the most likely termination step is going to be this coupling, right? Most of the radicals in the solution at any given time would be bromine. Now, again, any of the 2 radicals that are made, if they bump into each other, could come together in a termination step, right? Oh, sorry. That is spelled out for you right here. You are going to be responsible for this mechanism as well. So in chapter 10, you have one new reaction, radical halogenation with two different, right? So radical halogenation with either Br2 and light or NBS and light. And you have the mechanism that you need to know for the anti-Markovnikov addition of HBr. All right, so you are responsible for these mechanisms and these reactions from chapter 10. We're not really worried about the thermodynamics. That's an interesting conversation about why you don't really see this with anything but HBr. It's the thermodynamics are the most favorable there. We're not gonna worry about that. The stereochemistry, because it is a radical addition, if you make a chiral center, you're going to get a racemic mixture, meaning the bromine could add to either side. We've seen that a lot we see that with all of our radical reactions. We are skipping 10.11. We're not going to talk about radical polymerization. Polymer reactions are cool. They work through much of the same mechanism types: initiation, propagation, termination. And they make some interesting polymers, but you are not responsible for them. So you can skip through section 11. If you are going into chemical engineering, polymer reactions might be more interesting for you, as well as the petroleum process. We are skipping 11, 12 as well. Interesting reading if you're interesting. 10, 12. 10, 11, and 10, 12 are interesting reading, but you are not responsible for them. The last thing that we shall talk about in this chapter is synthesis. Now, we are going to spend a significant amount of Unit 4 talking about synthesis, but you have been introduced in chapters 8, 9, and 10 into the idea of multi-step synthesis. That's where we're headed. Chapter 11, that's all we're going to talk about. We've built quite a toolbox between chapter 7, 8, 9, and 10. Lots of new reactions, lots of functional group transformations. We have even a reaction where we can create carbon-carbon bonds. This is the only reaction you have that starts with an alkane. So if we have an alkane, we have only one way to go in the beginning, and that is to put a halogen. Now, I'm not going to pretend X2. You can put chlorine on it, but bromine is going to be the most useful. Right? If you have an alkane, now you are going to have something with functionality, right? A brominated alkane. So this reaction is hugely important for introducing functionality, right? So from here, you have a lot that you can do. If you start with an alkane, you can add bromine, and now you can do substitution reactions from chapter 7. You can do elimination reactions from chapter 7. From there, you can perform addition reactions from chapter 8. If you make a dihalide, you can then perform reactions to get you an alkyne, right? This is an entrance into all of the other chemistry that we've learned. So when you get to the end of your chapter 10 homework, there are some interesting multi-step synthesis problems to work through. If I give you more than a 2-step synthesis, it would be a challenge problem on this exam, a bonus problem. But it will be a large focus of Unit 4. So make sure that you are organizing this toolbox of reactions. Klein, great with some summary slides here of your new reactions. It's going to be really important when we get to Unit 4. You're going to need everything you've learned up till this time. So if you are someone that crams, and it's not a value judgment, I did it myself, it's important that you recognize you need to commit this stuff to your long-term memory. My Organic 2 students are still using their Organic 1 reactions. So stay organized. Keep your notes, keep your practice guides. If you're going to take Organic 2, it's good to have them with you in that class as well. And I will see you in Chapter 11.